All right, good afternoon, AP Chemistry. Today what we're doing is we're going to be talking about, we're going to be starting to go through, actually this is in Chapter 19. This is Chapter 19 in the new version of the book, sorry. This is Chapter 20 we're talking about today, which is about entropy and free energy. Now, you may remember last year that you talked about entropy. We said that entropy is kind of like disorder. We're going to talk a little bit more detail what entropy is probably than you did last year, but we kind of thought we'd start with this picture here on the front on this beginning slide, which is a typical bedroom right here. At least this is kind of resembling in cartoon form what my room used to look like when I was younger, so it's in a state of high entropy. So this is the first podcast in Chapter 20. If you are in periods 1 or 2, you are supposed to watch this and take notes and bring them to class with you when next we meet. And if you're in period 2, you'll have one fewer podcast to watch just because of the way that star testing is working out. Okay, so before we talk about entropy and free energy exactly, we're going to define something called spontaneity. All right, so spontaneity. When you describe something that happens spontaneously, it's something that just happens. It happens by itself. So in chemistry, okay, a spontaneous process is one that happens by itself. Okay, that has a tendency to happen or a tendency to occur. Okay, and there's a couple reasons why spontaneous processes happen. Another way you could describe a spontaneous process is one, if something is spontaneous, that means it favors products, whatever that process may be. So this is one where the position of equilibrium lies to the right. It favors formation of products, whatever that might be. And there's two reasons that a process may be spontaneous, or in other words, that it may want to happen. If you remember back to Chapter 6, we talked about thermodynamics and delta H and enthalpy. We said that certain processes want to happen. These are ones that are exothermic, okay? If something is exothermic, you may recall that it's releasing energy, okay? So one thing that makes a reaction spontaneous is that it's going to a lower energy state, okay? If you have a chemical system that through a reaction or through a process is going to a lower energy state, that also, that favors that process happening, okay? The second thing that favors spontaneity, that makes a process wants to happen, is that there's going to be an increase in disorder. Okay, well, in disorder, in chemistry terms, really disorder we're talking about here, this disorder is something called entropy. And it isn't simply disorder like clutter or being unorganized. It's really talking about, entropy really refers to dispersion of energy, which we're going to talk a little bit about. Okay, so but first, an example of a spontaneous process. This is a picture here over on the right-hand side of the screen that is out of your book. Just kind of show you what a spontaneous process is, one that occurs all by itself. In this beaker right here, what we have here on the bottom is solid potassium permanganate. If you remember your ions, you will know that potassium permanganate has a formula KMnO4. That is potassium permanganate. Now you see that here on the top beaker, right here, the potassium permanganate is purple, and it's mostly there on the bottom. You can kind of see here in the middle of the beaker, in the middle of this picture, that there's some purple pigment that's being dispersed into the liquid. That's because this potassium permanganate is starting to dissolve. And this picture must have been taken right after they put the solid into the beaker. Now, if you compare that here, if you let some time pass and you compare what's going on in the top beaker to what's going on in the bottom beaker, you can see here in the bottom beaker that there's a fairly homogeneous looking solution here where there's a purple color throughout. The reason why this is purple throughout is because as time passes, that potassium permanganate dissolves. So really what we have here is we have potassium ions, and then we have the purple permanganate ions here in solution. So you can see that we're not really doing anything to the system here in the top beaker. That potassium permanganate just dissolves all on its own. That's an example of a spontaneous process. This is dissolving. Okay, so let's go through, let's take a look. What is the second thing, entropy? We can understand something wanting to seek a lower energy state. That's one thing that makes something spontaneous, but the other thing is an increase in disorder, an increase in entropy. Let's look at what entropy is. Okay. All right, entropy. I've used this word several times. What does it mean? What entropy is, in thermodynamic terms, is a measure of the dispersal or the disorder of energy in a system. So, dispersal, what does that mean? Well, when something is dispersed, it spreads out. It turns out that if you look at a chemical system, energy has a tendency to spread out amongst the atoms and molecules that are in the sample. If you measure the entropy of something, what that is that measures how much that energy basically is spread out. It's kind of an ethereal concept, but we're going to look at a picture here that should kind of help you to visualize what exactly we mean by dispersal of energy, or this also sometimes correlates to dispersal also of mass, as we're going to see. Okay, it's measured in units of joules per mole dot Kelvin typically. Okay, now if you remember back to thermodynamics again, joules here, this is a measure of energy. So it shouldn't surprise you to see that if you were to calculate the change in entropy, we'll go into more detail on this later, the change in entropy for something, if you look at the change in entropy, the change in the disorder of the energy in that system over the course of a chemical process, that's calculated by dividing the heat transferred divided by the temperature. So it's joules per mole times Kelvin, so it's divided by temperature. That is how we measure entropy. So let's look at where entropy comes from. Okay, in your notes, Kelsey, you have a similar picture to this. I don't know if it's not really quite exactly the same. This is a picture that comes out of the next edition of your textbook. Now, to explain how entropy works and how this whole disorder works and how a system tends towards dispersal of matter and energy, we're going to consider a scenario. Here in the top of this picture, what we've got is this nifty little flask. Okay, so it has two sides. Initially, this right-hand side here is filled with a gas, and the right-hand side here is evacuated, meaning it is empty. Okay, and then here in the middle we have this valve that controls that can open it or close it. And so let's pretend here, just for the sake of argument, that over here, really we know this is a gas-filled flask. We're going to have a whole bunch of atoms and molecules in there, but we're going to pretend that this gas that's in here, just for the sake of our example, is helium. And we're just going to consider, just for the sake of argument, that there's 4 atoms of helium in this side of the flask. This is 1, 2, 3, 4. We're going to call this one, this is going to be A. This one right here is going to be B. This is going to be C. And this is going to be D right there. And over here, of course, there is nothing. Now, when we open this stopper right here, so we open it so that the gas is free to move back and forth between the two sides, let's think about what we expect we would observe. If we think about what we know about gases, we would expect that if we open it, since these particles are continually moving around here in this flask, we would expect that if we opened this stopcock here, and we looked at this flask some time later, that this gas that's trapped initially here on this side of the flask is going to spread out and is going to occupy both sides. So here in the second part of the picture, this is after some time has elapsed. So we know that this is a spontaneous process, actually. This happens by itself. The gas has a tendency to spread out because mass, just like energy, also has a tendency to be dispersed over chemical processes. So let's take a look at the different ways these atoms, we only have these 4 atoms here that are in this whole flask, just for the sake of argument. Let's have a look at how they can possibly be arranged, okay? Let's look at, this is what this diagram represents. This is out of a different textbook, the Zumdahl textbook. I just kind of stole this from there. Not stolen, but it's cited right there, so it's not plagiarism. This is a graphic out of the Zumdahl textbook. Now, if you can imagine, here's our flask, and here's our little valve that separates the two sides, okay? Now, if this valve is open and these gas particles are free to move between the two sides of the flask, there's a bunch of different ways that those gas particles can be arranged. If we were to look at this flask at any particular point in time, there is a small but a finite probability that we might find the atoms in this arrangement. It's possible, although it's unlikely, that we might see all 4 of the atoms, A, B, C, and D, on the left-hand side of the flask, and nothing is on the right-hand side of the flask. Okay? This has a comparatively low amount of entropy, this first arrangement. By the way, each of the different arrangements, there's a technical word that they use to describe these. These arrangements are called, in other words, microstates. So each way these helium atoms can be arranged as a different microstate. All right. So this is one way it can be arranged, and there's only one way this can occur, if all 4 atoms, A, B, C, and D, are on the left-hand side of the flask. Now there's another type of arrangement. We look at, there's a different different set of microstates, a different arrangement here. We could have it to where if you look at the left-hand side of the flask, we have 3 of the atoms on this side, and we have 1 atom on this side, okay? Now, if we compare this to the first arrangement, this has a higher degree of dispersal, or a higher entropy, okay? And if we look, there's 4 different ways we can have 3 atoms on the left and 1 on the right, okay? So we have it to where B, C, and D are on the left side, and A is on the right side. We can have it to where, if you look at the second right here, A, B, and D are on the left side, and then C is on the right side, or we can have these other ones right here. So there's 4 different ways that we can arrange it to where there's 3 atoms on the left and 1 on the right. If we look at the third set of arrangements, okay, there are 6 different ways that we can have 2 atoms on the left and 2 on the right. So this is another way we can have these atoms arranged. And there's 6 different ways you can have 2 atoms on the left. So for example, you can have atom A and B on the left and C and D on the right, or you can have B and C on the left and A and D on the right, or you can have A and C on the left and B and D on the right, etc. So those 3. In a similar way, if you look at arrangements 4 and 5, you can also have situations where 3 of the atoms have migrated to the right half of the flask and 1 is left on the left side. Or you can have it to where if you look at a particular instant in time, it's possible, although unlikely, that you can have all 4 of the atoms on the right-hand side. Now, if I were to ask you, okay, class, which of these arrangements is most probable? You would tell me, well, of course, Mr. Harper, the third arrangement is the most probable, okay, because there's 6 different ways we can arrive at having 2 atoms on the left and 2 atoms on the right. Whereas if you look at these other arrangements here, there's 4 ways you can have arrangement number 2, there's 4 ways you can have arrangement number 4, there's only 1 way each can have 1 or 5. And so if you look here at this middle arrangement 3, this is the arrangement where that has the highest probability of occurring. It is also the one that has the greatest dispersal of the gas particles. They're spread out the most in this way. This is the arrangement that has the highest entropy. Ooh, okay, my tablet's freaking out. Highest entropy. And by the way, as long as we're saying entropy, I might as well tell you the symbol. In thermodynamics, the symbol for entropy or disorder of the system is S. Okay? So this is the state that has the highest entropy, the highest dispersal of the stuff. And you can see, guys, that this all really comes down to probability. If you let these atoms these gaseous helium atoms just do what they want to do, they're going to have a tendency to arrive at arrangement number 3 because it is the most probable. Okay? And you can imagine that as we add more and more and more and more and more atoms here to this system, that the probability of achieving this sort of a state where you have the atoms equally distributed and maximally spread out is going to become higher and higher and higher. So you can see this whole idea of entropy, or the spreading out of matter, is all about statistics. It's all about what is most probable the system is kind of left to its own devices. So now, of course, being AP students, your next question is going to be, well, Mr. Harper, do I have to be able to describe this on the test? And the answer is, well, probably not. I'm not going to ask you for a statistical explanation of why entropy happens, but this is kind of for your edification so that you understand what entropy is. Okay? So this is kind of using an example showing the dispersal of mass. In the same way, we can also make an argument that describes the dispersal of energy in a system. So just kind of follow me with this, guys. Assume here for a second that we have our 4 atoms, okay? Atom A, atom B, atom C, and atom D. Now, imagine we put these atoms all in a flask together, and these atoms here, B, C, and D, have all got an energy of, just say for the sake of argument, they've all got an energy of 1 joule, and 1 joule, and 1 joule. And these are all in a flask together. And say atom A here has got a lot of energy. Say this has got 10 joules, okay? Well, what's going to happen here? Atom A has got a high amount of energy here at this particular point in time when we start, right? We put all 4 of these atoms together, but it's not going to stay that way. You can imagine if we put these 4 atoms into one side of one of these flask bulbs here, so they're all contained into one side here, what they're going to do is they're going to fly around and they're going to run into each other. So this 10 joules of energy is actually going to get transferred to atom B, and to atom C, and to atom D. In other words, that energy is going to get spread out amongst the atoms that are there in the sample. Okay, a measure of that spreading out of the energy is the entropy. And yeah, so just has, basically this is just the idea that it has a tendency to spread out. Energy will spread out, and matter, is also going to spread out. So that's kind of the overall point of all this. Okay, so the point. In a spontaneous process, so again, spontaneous, for all spontaneous things, these are things that happen by themselves. All chemical processes that happen by themselves, okay, the entropy of the universe always increases. And this is the second law of thermodynamics, guys. This you should be familiar with. The second law of thermodynamics says that the entropy of the universe is always increasing. So in other words, if we're looking at chemical processes that happen by themselves, so this could be things like melting ice cubes, this could be burning wood, this could be respiration. All these things are chemical reactions that are spontaneous. Okay? In a spontaneous reaction, disorder tends to increase. Okay, and that is the point. All right, so the next natural question is, well, how do we calculate entropy, Mr. Harper? How do we define entropy? Well, just like when we talked about heat, I can't look at somebody in class and say, well, Paul, you have so many kilojoules per mole of energy. I can't just say you have X much heat. In just the same way, you can't look at something and say it has this much entropy. We have to measure it relative to something. And so there's a guy named Ludwig Boltzmann. We'll talk a little bit more about him later, who was kind of the person who developed this idea of entropy and the mathematical relationships going along with it, who said that, okay, well, by definition, we have to have a standard. We have to have a reference to measure things against. So we say that the entropy is 0 for a perfect crystal at 0 Kelvin. So say, for example, I take methane, okay, and I cool this down to 0 Kelvin, which is impossible, and I had a perfect crystal of methane at 0 Kelvin. We would say that for methane at 0 Kelvin, the entropy is exactly 0 joules per mole Kelvin. Okay, that is exactly nothing. It has no entropy at all because it's perfectly ordered. So at room temperature then, we're basically measuring, you know, if we want to find then the standard enthalpy, or the standard entropy. So you remember, guys, if you see this little degree sign symbol, what that means is it's measured under standard conditions. So it's 1 bar of pressure and 25 degrees Celsius. If we're measuring the standard enthalpy, sorry, I keep saying enthalpy, but it's entropy, the standard entropy of methane, what we're really measuring here is the disorder or the dispersion of the energy in methane relative to that perfect crystal. So what we're going to do now is we're going to go through and we're going to compare the entropies of different states of matter and different types of substances to kind of, you know, get a feel for which things have the greatest amount of disorder, the most freedom really, and most dispersion of energy in their structure. Okay, so the first thing is for solids, liquids, and gases. Okay, let's think about which of these has the greatest amount of disorder. And you'll tell me, well, Mr. Harper, this is obvious. Gases, of course, has the greatest amount of disorder. Let's think about why that is. If we look, just for the sake of argument, we'll look at helium again because helium is easy to draw. It's just a sphere. Helium, if we look at the solid state, okay, we could think about if we were able to solidify helium, which we've never done, but say we were, okay, if we were to have solid helium, what it would look like is we would have a regular arrangement of the atoms here in kind of a solid crystal structure. And so those atoms would be packed very, very, very close together. Now, if you remember, in a solid, okay, what defines a solid state is that these atoms are very close together and they have very little motion. They do move, but they only vibrate in place. They don't move translationally. They're not moving through space. They only vibrate a little bit. And so if you look at a solid structure, there's relatively low entropy in a solid because the particles can't move around very much. Whereas we compare that to a liquid. Oop, I can't spell. Let's call this a liquid. Also, just for the sake of argument, we're going to draw this being in a beaker. And on that beaker, we're going to put a lid. Okay, so just kind of imagine that. So, ooh, didn't want to do that. All right, so here's a beaker, and we have our liquid. Now, the difference here in a liquid is the particles are a little further apart, not necessarily a whole lot further apart, but the difference, guys, between a liquid and a solid is that in a liquid, and I'm just going to stop drawing. You can kind of, think, you can extrapolate on your own. You can think that these particles are not just moving vibrationally, they're also moving translationally. They're moving past each other because the intermolecular forces of attraction have been broken down to a certain extent. So if you look at the relative amount of disorder, or the dispersion of the matter and the energy in a liquid, it's going to be higher than for the solid. So there's a great amount of disorder of the energy of the system in a liquid. And so this has got a higher entropy. If we were going to compare just helium, the entropy of liquid helium is going to be higher than the entropy of solid helium. Whereas, now let's compare that to a gas. You know that the difference, guys, between a gas and a liquid now is that in a gas, these particles are going to be very far apart, and they're also going to be moving very quickly past each other. So they're really moving. Okay, they're hauling, going past each other. So you can think that for a gas, the entropy of the system is going to be way higher. So this is going to be the highest entropy state of matter right here is going to be the gas. So if you were going to rank solids, liquids, and gases, okay, the gas has the highest entropy, more so than the liquid, which is going to be, again, more so than the solid. Because mostly here, guys, again, if you are taking or have taken statistics, it's kind of a degrees of freedom kind of thing. These are more free, the particles in the gas are more free to move around, hence there's more disorder. The more degrees of freedom, the freer things are to move, the more disorder there is, and so that's the highest entropy state right there. Okay, so that's all looking at the gas. Let's go on and look at other things. Okay, how about different molecules? We compare simple and complex molecules, which has a higher entropy. Okay, the tendency is, guys, that the entropies of complex molecules are greater than the entropies of simpler molecules. So for the sake of example, let's compare methane and ethane and propane. We can think, obviously, which of these will have the higher entropy? Well, methane, of the three hydrocarbons pictured here, is the simplest. It's 1 carbon and 4 hydrogens. Ethane is the next most complicated, and propane is the next most complicated. And as we go down, we can see that the entropy of methane is 186 joules per mole Kelvin, of ethane is 229.2 joules per mole Kelvin, and propane is 270.3 joules per mole Kelvin. So you can see, guys, that as we go down this list, the entropy is increasing. Okay, the entropy goes up as we go down this list. And the reason is because as we go to more and more complicated molecules, okay, so from ethane to ethane and then from ethane to propane, these molecules become increasingly more flexible. There's more ways they can bend, there's more ways they can rotate, there's more ways that they can, basically there's more degrees of freedom, we can say. They can do more things, there's more ways they can move around, and so hence there's more disorder that's possible in propane. If you think back to our picture with the beakers and talk about different ways the atoms can be arranged, for propane there's a much greater number of ways these atoms can be arranged in space due to rotations about bonds. You think about this bond rotating, okay, that bond can rotate around, so the atoms can be arranged a bunch of different ways. Whereas for methane, there's really not so many degrees of freedom, so many ways the atoms can be arranged. So the more ways, the more arrangements that are possible, the greater the amount of entropy. Okay, next. Let's look. Okay, we already did that one, so that's kind of a repeat. Sorry. And, okay, next thing. The entropy of a system generally increases. That's the fill in the blank there. When a pure solute dissolves in a solvent. All right, let's think about, again, why that is. Let's think, just for a moment, about what happens when we take some water, and then we dissolve in there a crystal. We'll draw a couple crystals here. Pretend those are crystals. These are going to be crystals of sodium chloride. All right? Well, to start with, before we put that sodium chloride in the water, those crystals of sodium chloride have got a very regular arrangement of the ions, those sodium chloride ions that make it up. It's a very, comparatively, if we look at that crystal, right, that crystal has got a lot of order. It's a very ordered system, so the entropy is going to be comparatively low. If you remember back to crystal structures, right, so we got alternating sodium ions and chloride ions and a sodium ion and a chloride ion. Very regular structure. Now, when we take this crystal and we dissolve it now in the water, what happens? Well, this order gets destroyed, and these ions, the sodium ions and the chloride ions, get dispersed in the liquid. So we have sodium ions and chloride ions and sodium ions and chloride ions all distributed here in the liquid. And that regular structure is gone. So the disorder of the system has increased. And so the entropy of the system increases when you dissolve something, the pure solute, in a solvent. Okay, other systems where we see a change in entropy, or others where we see a change in entropy, are things like this. Generally speaking, entropy increases when a dissolved gas escapes from a solution. Now let's think about why that is. A good example of this is my favorite beverage, which is Dr. Pepper. Dr. Pepper is a soda. Dissolved in that soda are molecules of what gas, guys? And everybody says carbon dioxide. Carbon dioxide. Okay. Well, we just said that when you dissolve a pure solute, so like something like sodium chloride in water, that actually the disorder increases. Well, the gas never really had a large degree of order to begin with. And actually, if you think about it, when that's dissolved in the liquid, there's a whole lot, you know, there's less dispersal of those gas particles than if these gas particles are allowed to escape. So if these carbon dioxide molecules move out and they go out into the air, well, what are they going to do? They don't all stay in one place. They spread out. They're going to diffuse. As we know, they're going to move all over the place. And so they're going to spread out, just like we said before. The more spread out something becomes, the higher the entropy is of the system. And so we can say again here that S is going to increase if that gas comes out, because there's going to be more disorder when that gas is out of the solution. Okay. Last thing, guys. This is really important to remember, because on the AP test, one of the things you'll have to do is estimate. Is something to be spontaneous, and if it is, why? Or is the entropy of a system increasing or decreasing, and why? Well, one thing you have to keep in mind, and this is very important, is that gases have a very large entropy, or have very large entropies, okay? The more gas you have, the more disorder you have, because those gas particles, like we've been saying, they want to spread out, they're going to go every place, okay? So if you have a chemical reaction where the moles of the gas that you have increase, okay, then in that system, where if you have the number of moles of gas going up, then the disorder is going to go up, because you're going from a relatively ordered thing to a relatively unordered thing. Let's have a look at how that might work. Okay, so consider the reaction. We have, say we have this thing, dinitrogen tetroxide, N2O4. It's a gas we've used for many examples in the past. And this, we know, will spontaneously decompose to give us 2 units of NO2. Now, without knowing whether or not this is an endo or exothermic process, without knowing anything about the heat and whether it's really seeking in a lower energy state, we can say that this has a tendency to occur. That this one thing that favors this being a spontaneous process is the fact that if we look here, the entropy is going to go up. To begin with, we have 1 mole of gas. On the reaction side of the equation, in the products, we have 2 moles of gas. Because the number of moles of gas is increasing, the disorder of the system is going up, and the entropy is increasing. Okay, so that's one more thing to keep in mind. As the number of moles of gas go up, like for example in combustion reactions, it happens frequently that the number of moles of gas will go up, the entropy of the system also is going to be increasing. One more situation, I forgot to put this on your note, skeleton guys, that you want to write down. Entropy always increases as temperature goes up. So as temperature increases, typically the entropy of the system also goes up. Now, we can think about that again because as temperature goes up, the motion of the molecules speeds up. They're moving around faster, moving around more. They're vibrating more violently. And so the more they're moving, the higher the disorder of the system. All right. Now, let's look at how we could calculate entropies. We're going to do an example to show you how to calculate. Oh, no, wait, hold on. This is not the calculated one yet. Never mind. We're going to just do some prediction here really quick. So what we're going to do here is we're going to predict the sign of the entropy change for these different processes. Delta S, okay, delta, anytime you guys see a delta, guys, that means change. Delta S is going to be the change in entropy for the process. So if we look at the chemical process, is the entropy going up or down? If the entropy goes up, the sign of delta S will be positive. If the entropy is going down, it's decreasing, delta S will be negative. Okay, so for the first one, letter A, we're going to predict. Does the entropy increase or decrease? Delta S positive or negative for this reaction here. So let's look. We have 2 moles of carbon monoxide here on this left-hand side, plus a mole of oxygen yields 2 carbon dioxide gas here on the product side. If we look at this, using the information we just learned, here we have all gaseous reactions. On the left-hand side, we have 3 moles of gas. On the right-hand side, we have 2 moles of gas. So because the number of moles of gas during this reaction is decreasing, that means that the disorder of the system is decreasing. And we can say that delta S for this process is going to be negative. Actually, the disorder is going to be decreasing because we have less gas. Okay. Letter B. This is actually the hydrolysis of water. We're going to do this when we talk about electrochemistry. We're going to split water into the elements. So we have 2 liquid water here goes to 2H2 plus O2 gas. Using the same arguments as before, if we wanted to predict what's the sign of the change of, or the sign of the entropy change delta S of this reaction, well, here we can see on the left-hand side we have liquid water, and on the right-hand side we have not just more moles, but also we can see that we've produced more moles in the product side, but also these are going to be a gas. So we're going from a liquid to a gas. Now we said that a liquid was more ordered, a gas is more disordered. So as you go from liquid to gas, disorder is going to increase. And so we say that delta S for this process is going to be positive. So if you can predict that, you're all right, let's look at how to calculate delta S. So to calculate the entropy change for a reaction, there's a formula you're going to use, the delta S. So we can say the standard entropy change for a reaction. This is going to look fairly familiar to you guys. Okay, it's going to be the sum of the standard entropies of the products. Minus the sum of the standard entropies, of the reactants. Okay, so let's look at an example of how you can apply this formula. This is something, it's kind of easy to remember because this looks exactly like when we were using heat formation before to calculate the standard entropy change. Exactly the same thing. Okay, so the example says, calculate the standard molar entropy change, which is delta S, the change in entropy, for the formation of gaseous propane, C3H8, at 25 degrees Celsius, and kind of implied as the formation, this is, again, if it says formation, a reaction that is a formation, that means from the elements. Okay. So from the elements. So the reactants here, guys, we know we're making C3H8. That, by the way, is propane. C3H8 over here. And we're going to be making this here from carbon and also from hydrogen. Now, when we write a reaction for a formation, again, this is going to be the most stable, naturally occurring form of the element. So hydrogen is going to be a gas. When we balance this, we got to have 4 molecules of H2. Carbon is a solid, but it is also graphite. It's the most stable, naturally occurring form of the element. Just a little bit of review there for you guys. Okay, so we have three graphite and 4 hydrogen gas gives us 1 molecule of propane. Propane, by the way, guys, is a gas. Okay. Now, so what we're going to do is to calculate delta S, use this formula. We're going to find the molar entropy of propane and subtract 3 times the molar entropy of graphite and 4 times the molar entropy of hydrogen. So let's do that. And you're going to say, well, Mr. Harper, if only I had a table of selected thermodynamic values. Well, that, guys, is in Appendix K. So if you're looking for where can I find the standard molar entropy of these different things, you're going to look at Appendix K. If you do that, you're going to see that the standard molar entropy of propane, if we scroll down there, is going to be 269.9 joule mole. Ooh, that's not what it's supposed to do. Okay, mole Kelvin. That's the products there. Okay, minus the sum of the molar entropies of the reactants. Okay, so we have 3 moles of graphite. If you look under carbon graphite, the standard molar entropy of graphite is 5.740 joules over mole dot Kelvin. Now, this may surprise you. I just want to point this out really quick. If you remember, if you look at the standard molar enthalpy, or the enthalpy of formation of graphite, it is 0. Okay, but everything, the standard molar entropy of everything, unless it is a pure crystal at 0 Kelvin, is always going to be a positive value. So notice this is not 0. The other thing to kind of take note about these values, if you look in the tables, is that they are all positive, that there are no negative entropy, standard molar entropy values. Okay, so 3 times the entropy of graphite, 4 times the standard molar entropy of hydrogen. If we look there, hydrogen, H2, as a gas, is 130.684 joules over mole dot Kelvin. And if you kind of compare the magnitude of these values here, you see that for hydrogen, this is pretty high. Okay, that is a very high molar entropy. And if you compare it, these are both hydrogen and graphite are both relatively small. You can see that the gas has a way higher entropy. Okay, guys, now it's time for calculator work. Alrighty, guys, if you go through and do this on your calculators, you see that delta S, the standard molar entropy change for the reaction, is going to be negative 270.056 joules per mole times Kelvin. Okay, now if you look here at this number, you can see that the standard entropy change is negative for this reaction. Now, why is that? Let's rationalize it and see if that makes sense. In this reaction, we start here with 3 moles of carbon and 4 moles of hydrogen gas. This is all going to a gas. This is true, but the numbers of moles of the gas is decreasing. We have 4 moles here on the reactant side. We have 1 mole on the product side. The number of moles of gas is decreasing, and so also the disorder of the system is going to decrease, and rationally the entropy should also decrease. So there you go. That is delta S. It makes sense. And that, guys, is the very end of this first podcast. So hopefully this has helped you understand what is entropy. The next podcast is going to be all about free energy. So have a nice day away from chemistry, all you guys, and I will see second period on Thursday and first period and second period, both you guys, on Friday. Have a nice time. I'll see you in class.